Introduction. In studies of aerodynamics, few engineers have access to full-scale wind tunnels or actual airborne laboratories. Most rely on what is probably the most common tool for aerodynamic study, the laboratory-based wind tunnel. This tool gives accurate results as long as the scale effect and reduced Reynolds number are taken into account. The AF1125 apparatus is a compact bench-mounted and practical open-circuit subsonic wind tunnel. The air passes through a settling chamber before entering the tunnel through an aerodynamically designed contraction that accelerates the air in a linear manner. Then enters the working section, finally passing through a grill before moving through a diffuser and into the variable speed axial fan. The grill protects the fan from damage by loose objects. The air leaves the fan, passes upward through an exhaust duct unit, and then back out to the atmosphere. The air velocity in the working section is controlled by the fan drive control in the separate control box. Apparatus description. The working section. The working section is of a square section with an acrylic roof, floor and sides. The whole unit is supported in an aluminum framework. One side panel and the floor have holders to support wind tunnel models. On the top of the working section are two pitot devices, and on the floor are two wall tabbings to measure the static pressure upstream and downstream of the working section. The two-component balance. The balance is mounted on the side of the working section, while the cylinder in this experiment is held inside the working section and is attached to the balance. The balance is connected to a separate control box and measures the drag force applied to the cylinder in Newton. The inclinable multi-tube manometer. The wind tunnel has pressure tappings and two pitot devices connected to a multi-tube manometer. The manometer is also used to measure the pitot and static pressures to calculate the air velocity. This manometer uses colored water as its working fluid and has a scale calibrated in millimeters to give a clear direct readings of pressure in millimeters of water. The manometer has 6 tubes all open to the atmosphere at their top, but connected to a common manifold at their base. The manifold connects to a reservoir at the side of the manometer. The reservoir has its own tabbing to help fill it with the fluid and normally left open to the atmosphere. The reservoir has a height adjustment for setting the datum or reference for all manometer tubes. Please use the bubble level to make sure that the manometer is horizontal. The tested model in this experiment is a cylinder with a pressure tapping. The diameter of the cylinder is 20 millimeters and its length is 123 millimeters. The control box. The control box contains the following: the main electrical isolator for the apparatus, the controls of the variable speed motor connected to the fan, the red emergency stop button, and the display for the two-component balance. Experimental procedure. The objectives of this experiment are: investigate the relationship between Reynolds number and the drag force. Calculate and compare the drag coefficient value in 3 different ways. First, by direct measurements. Second, by the pressure profile. And third, by using wake traverse. Finally, the student will compare the calculated values with what is available in the literature. Before using the multi-tube manometer, let's first learn how to read the pressure values. In this example, pressure P1 and P2 are above the atmospheric pressure, while pressure P4 is below atmospheric pressure. The manometer measures the pressure in millimeters of water and should be converted to pascals. To do so, multiply the pressure readings in millimeters of water by 9.81. To increase the sensitivity of the manometer so small pressure changes can be seen more clearly, all experiments should be done by adjusting the manometer angle to 30 degrees. This can be done using the pointer and angle scale on the side of the manometer. The correct pressure values can be calculated by multiplying the measured values by cosine 30 degrees. The experimental procedure starts with preparing the display and the balance. First, turn on the control box. The control box display will show you the force reading. Now leave the control box to stabilize for at least 5 minutes. Make sure that the cylinder module is set up correctly. Then press and hold the 0 button for at least 4 seconds to re-zero the force reading. Now you can start the experiment. Experiment number 1. Direct force. Create a blank result table similar to what is available in the manual. Record the air temperature and ambient pressure. Set the protractor to 180 degrees angle. Now set the manometer to 30 degrees to increase resolution and accuracy. Zero the balance. Switch on the fan and adjust the airflow to a low level around 1 rotation. Record the drag force and the pressure PO from the upstream pitot traverse and the static pressure PC at the upstream wall. Also record the pressure at the measuring point PM and the static pressure PA at the downstream wall. Increase the airspeed in 6 increments up to the maximum speed. In each time record the pressure readings and the drag force. Try to get at least 7 sets of results to give a reasonable graph. Experiment number 2. Measuring the pressure distribution around a cylinder. Create a blank result table similar to the one shown in the manual. Now set the manometer to 30 degrees to increase resolution and accuracy. Zero the balance. Record the air temperature and ambient pressure. Set the airspeed to maximum and the protractor to 0 angle. Fix the upstream pitot traverse around 30 mm below the top wall. Make sure that the pressure tapping is facing the airflow directly. Record the difference between the cylinder surface pressure, PM, and the pressure, PC, at the upstream wall, and take the drag force reading from the force balance. Rotate the protractor in 5-degree intervals, and repeat the previous step. Please note that it is important to monitor the difference between the total pressure, PO, at the upstream pitot traverse and the static pressure, PC, at the upstream wall to ensure that the airspeed remains constant throughout the experiment. Experiment number 3. Using the wake traverse. Create a blank result table similar to the one shown in the manual. Record the air temperature and the ambient pressure. Set the airspeed to the maximum. Now set the manometer to 30 degrees to increase resolution and accuracy. Traverse the downstream pitot device across the section from the top to the bottom in increments of 2 mm near the center, increasing to 5 mm towards the sides, where the total pressure becomes fairly constant. Write down the downstream pressure difference of PE and PA after each increment. Continue lowering the pitot tube with the indicated increments in the manual and record the pressure values. Shutting down the wind tunnel. Slowly lower the fan speed by turning the speed control fully counterclockwise. Now you can press the stop red button or the emergency stop button. In case of emergency, press the red emergency stop button, turn the speed control fully counterclockwise and inform your TA.